This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Is minus 1 upon rho t. So you have a t here, and this is a 1 upon rho here. And so the s dp when this is 0 is minus 1 upon rho t. And so s increasing, if ds is positive, then for an increase for this to be negative, then the pressure has to decrease. dp, delta p has to be negative. And so what that tells you is that the total pressure, P, or the reservoir pressure, if I go from upstream to downstream, has to fall. If it's isentropic, it will be constant. The total pressure will be constant. So, so S increasing, which I showed you, no? Right. So only if there is no dissipation, flow everywhere is in equilibrium, then it is true that the downstream entropy, S naught prime, is equal to S naught. And since H naught prime is equal to H naught, then it follows that P naught prime, the downstream reservoir pressure, is the same as what it was upstream. And then I say here that the reservoir conditions, H naught and P naught, etc., are often called stagnation or total conditions. And the local stagnation or total condition is the condition that would be obtained if the flow were brought to rest locally, isentropically. So this is a very important idea. And that total, those local total conditions are called PT, HT, and ST. And for total conditions to exist, it is not sufficient to bring the fluid to rest. You need equilibrium also. That's to say, the total temperature is difficult to measure because even though you bring the fluid to rest, typically you do it in an environment in which there are large surface stresses or large heat transfer in the fluid. So I summarize this for you here, that HT, the local total conditions, are equal to H naught, the reservoir condition, the upstream reservoir condition. And that's all you need is for the process to be adiabatic. You're not adding any heat or doing any work. The total entropy, ST, is by definition the entropy, the local entropy, S, because you're bringing the fluid to rest isentropically. So HT is equal to H naught, which means that the total temperature is T naught, and the speed of sound, the total speed of sound is equal to A naught, and that's true for an adiabatic perfect gas. Only if it's isentropic will the total pressure be the upstream reservoir pressure, the total density be the upstream reservoir density, and the total entropy will be the static entropy, which will be equal to S naught. In general, if the flow is adiabatic and not isentropic, then the total pressure is less than the upstream reservoir pressure, the total density is less than the upstream total density, reservoir density, and the entropy is locally higher than S naught. Now, is there anybody here who doesn't understand what I've just done? Because this is a very important idea. What are total conditions and what is the reservoir condition? And you can see it, and I'm going to illustrate it for, say, a gas turbine, and or for a heat exchanger, or for a compressor, or for a combustor, I mean. And I've schematically just illustrated what those devices might look like. This is where you're doing work in the compressor. This is where you're doing adding heat in the combustor. And so now, let's go back and why I spent so much time talking about the conservation laws themselves. Because it's the heart of the matter. You have to know these conservation laws. So let's remind ourselves. So for steady flow, meaning that the rate of change at any point, the partial derivative with time, is identically zero. So it's steady flow. If that's true, then the energy equation is the mass flux rho u dot n times the h plus a half u squared, because h is not only the internal energy but the pressure work. So h appears there because you've already included the pressure work. But in general, there will be an integral over the bounding surface of tau ki ui nk ds, and there will be a change in that left-hand side if you're adding heat or if you're doing work. So that's the energy equation. And as I said to you several times, this tau ki ui nk is often neglected, or it's very nearly zero. And it will be identically zero on walls because the ui will be zero. There's no velocity at the wall. But it's also true that on normal surfaces to the flow, then this tau ki nk will be, for example, tau xx in the x direction, or minus tau xx. And tau xx is 2 mu du dx, and so if there's no gradient in x for the streamwise velocity, it's identically zero, and it does no work. All right.
For unsteady compressible flows.
Yes.
Would that term also tend to zero?
Yes. It wouldn't be on the normal boundaries, no, because now. Well, it could be because the u dx could still be zero. That's to say, if I had constant area and there's no change in the velocity there, where I drew this boundary, then tau xx would again be zero, because it's 2 mu du dx. All right, now we have, in addition to the steady flow energy equation, we have the conservation of mass, which we have to write down, and that, because there's no d rho dt, it says that the integral of rho u dot n ds is identically zero. Now for this device, we're going to assume uniform flow at the inlet and uniform flow at the outlet, so that we can easily do this u dot n ds. It's simply the velocity time in the direction of the normal, and it'll be minus, for the upstream condition, if this is the upstream condition here, it'll be minus rho 1 u1 a1. Why? Because the normal is in that minus direction, but the velocity is in the opposite direction, so u dot n is minus 1. So it's minus rho 1 U1 A1 plus rho 2 U2 A2. And frequently, we will use rho UA as just m dot. So it says, so this equation here would be minus m dot H1 plus a half U1 squared plus the potential energy, and plus on the downstream condition, we'll have m2 H2 plus a half U2 squared plus V2 is equal to the heat supplied to the volume and the work done in the volume, W dot. So now, usually this difference in Phi1 and Phi2, if you were talking about a horizontal device, then it would be negligible. Even a vertical device, if you're talking about a water pump, for example, it's probably going to be relatively small, so we can neglect it. And if you do neglect the change in the potential energy across in the control volume you're talking about, then this equation, H1 plus a half U1 squared, is by definition the total enthalpy, H2T. So this is H2T on the left, here in this term here, and this is H1T, and it'll be m dot into H2T minus H1T is Q dot plus W dot. That's incredibly simple. Incredibly simple. And then if I simply divide those rates of heat supplied and rates of work done by the rate of mass flowing through the device, I get what I've called lowercase q and lowercase w by definition. And then the difference in the total enthalpy at 2 minus the total enthalpy at 1 is simply q plus w. So let's do something now for a compressor. Let's supposing we were talking about the compressor in a gas turbine. So to a good approximation, no heat is being added in the compressor. No heat's being extracted in the compressor, to a good approximation. Then we can write down that TdS is dH minus dP over rho, or that dH is dP over rho plus TdS. So that says that this difference in total enthalpy will be least, because this will be greatest, if I'm given a delta P. This delta H will be least if delta S is 0. So the change in the total pressure divided by the density and the change in enthalpy will be least if delta S is identically 0. So that is the definition that's used for the efficiency of a compressor, that is not compressing water. Well, we can use the same expression, and I'll show you it for an outboard engine. I'll show you in a minute, for an outboard engine on a speedboat. So how would you use this definition of efficiency? You would do it in this way. Let's suppose that I want to take the pressure from some value P1 to some value P2. Then the least amount of work that I will do is when the entropy doesn't change. So I go from S1 to S1, but I go from P1 to P2. And it'll be the least work that I have to do, and for some reason this is not quite in the center here. Maybe I can make it so. How can I just move this screen over? Oh.
Yeah,
Right. So here's the summary of what I'm saying. For a given pressure rise, so this is the definition of a compressor. For a given pressure rise from P1 to P2, the least amount of work that I have to do is when I do it for the same entropy that I started with. So that's S1. But the actual work that I have to do takes me to a same final pressure ratio, but I finish up at a different entropy. Because in this compressor, I have boundary layers, and the boundary layers introduce viscous losses. So I have viscous losses inside the real compressor. So how big is this efficiency? What would you guess for a modern gas turbine? Would you have expected 40%? After all, the efficiency of those thermal engines that Watt's thermal engine was 0.5%. 0.5%. But a modern gas turbine is up at around 85 to 90% is the efficiency. And for a turbine, not a compressor, for a turbine, the efficiency is higher. Why? Why would the efficiency of a turbine be higher than the efficiency of a compressor? Somebody guesses. Guess. Why? Nobody bold enough to even hazard a guess. Why do you think one is higher than the other? Well, because a turbine will drop the pressure because you're going to take work out of it. The pressure will be falling, and all those boundary layers, you won't get separation in the same way. Whereas in the compressor, the boundary layers are likely to face rising pressure, and they're likely to separate. And you lose more efficiency if the boundary layers get thick and separate than if they don't. So that's why that's true.
Is that also related to the temperature?
Is that true? Beg your pardon?
Is that also related to the temperature? Because in a turbine efficiency and compressor efficiency, in thermodynamics we use the temperature like.
Yes, because. Yes, indeed. I mean, these total conditions are, in fact, the total enthalpy. For if it were a gas, you know what the total enthalpy is in terms of temperature. So it's a statement of the temperature. Yes, exactly. You're essentially finding the enthalpy by finding what the temperature is, by measuring the total temperature. And you're trying. So here's an illustration of a compressor. Here's an illustration of it. You can see that I start at S1, and the least amount of work, if I get from, this is a typical HS diagram and a constant pressure line in a Mollier diagram looks like that. So this is a Mollier diagram. H is a function of S, and P is P of these lines. And so we start here at this entropy, and actually our reservoir conditions, P1 naught, is right here, and the total enthalpy corresponds with that. So I bring the fluid to rest, and I measure the total temperature. And that's not so easy to do. In principle, you can do it with a thermometer, and you bring the fluid to rest. But as I've said to you, one of the subtleties is that when you try to measure the total temperature, you're bringing the fluid to rest, but if you're actually got large gradients in large stresses or large heat fluxes, then it won't be the right total temperature. So, but anyway, let's supposing that's what we did. So we want the total enthalpy at condition 2. Now, if the entropy increases, and we still have to get to this higher P20 here, this higher pressure, then the path that we've taken is gone from here to here, whereas the least work would have been from here to here. And now I want to do something for you. What constitutes a small pressure rise? So, for example, if I were talking about water, how would I work this out for water? And I'm about to do it. What if it were a windmill? What if it were some kind of windmill that's taking power out of the air, not putting it in? Or it's some kind of incompressible pump, like a propeller. So let's remind ourselves, H2, so for the ideal pressure rise, HT at the second condition is P2 at the second pressure, but the same entropy as the total enthalpy at 1. Now we can write that difference as dHdP at S1 delta P plus a half d2HdP squared at S1 delta P squared plus higher order terms, right? So you can just do that Taylor's expansion. But you saw that TdS was dH minus VdP, or that's the thermodynamic identity, so that at fixed entropy, TdS, the left-hand side is 0, so dH/dP at fixed S is automatically the specific volume V, which is 1 upon rho. So I can work out d2HdP squared, and so I just differentiate that with respect to P, and that's minus 1 upon rho squared, d rho dP at fixed entropy. But what is dP d rho at fixed entropy? Well, I'm going to do it later today, but does anybody know from any other course, anything you've ever done in your life, what is dP d rho at fixed entropy? Nobody knows? Nobody? Not one of you knows that dP d rho at fixed entropy is, it obviously has the units of a velocity squared, because the pressure, P in the Bernoulli equation, P over rho plus a half U squared. So dP d rho will have the units of a velocity squared. And it's by definition, A squared. It's just going to be called A squared. And A is a function of temperature and so on. We're going to work that out later. So d2HdP squared will be minus 1 upon rho squared. D rho dP at fixed entropy is 1 upon dP d rho at fixed entropy, which is A squared. So this is minus 1 upon rho squared A squared. So going back here just quickly, why is this? I'm sorry. So I have this expression here for, no, the one before it. So I've got, if I pull out the delta P here, and the HdP is 1 upon rho. So the first term here in a Taylor's expansion will be delta P over rho. Why does this thing keep bouncing around? Sorry, nearly there. Right. So this Taylor's expansion, the first term will be a delta P over rho, and the next term, d2hdp squared, will give me a delta P, so I'll have a delta P squared and a half, and I'll have a rho squared. I'll have a rho squared a squared, and I pulled the rho out in front, so it's delta P over rho into 1 minus delta P over 2 rho a squared, plus the next term will be ordered delta P squared. So how big is this term here? Well, let's look at rho a squared for water. For water in SI units, the density's about 1,000 kilograms per cubic meter, and the speed of sound is about 1.5 or 1,500 meters a second. So that's 1.5 squared by 10 cubed. Squared is 10 to the 6th. And so if this is about 2, and it's 2.25, but it's about 2, and then I've made this 10 to the 4th and this 10 to the 5th, and 10 to the 5th you would know in newtons per meter squared is atmospheric pressure. So for this term to be large, delta P over 2 rho a squared, for that to be a significant term, I've got to get up to very, very high pressures, like 20,000 atmospheres. But if you were cutting rock with a water jet, you'd be at that pressure. With a water jet, you'd try and get right up to near the speed of sound in water. Whereas in air, this rho a squared, rho is 1.18 kilograms per meter cubed, and a is about 350 meters a second, so that's squared, and I just worked that out, and it's about 1.4 by 10 to the 5th, so it's about 1.5 atmospheres. So the least work is the change in the total pressure divided by rho, and that's the change in, that's this term here, and now we've got to worry about whether this term's significant or not. And so if that term is not significant, like for example a propeller screw for an outboard motor, then this term is not going to be significant, and it's simply going to be the ideal amount of work is m dot into this change in enthalpy, which will be P2T minus P1T. That's the delta P divided by the density. And let's see what that is. So the actual amount of work is the ideal amount of work divided by the efficiency. And so here's a propeller in water. And I wanted you to I wanted you to be able to see it quickly. So here's this propeller. So the ideal amount of work is the total pressure here, minus the total pressure here. But approximately speaking, going through this propeller, the actual streamline velocity is not changing locally here. But the pressure is, because the propeller's pushing on the flow. So you would like to say that the total pressure here and here, let's work out what they are. The final total pressure, P2T minus P1T, is P2 plus a half U squared, where U is the velocity through the propeller disc, minus P1 plus a half U1 squared, which is just the difference in static pressures through the propeller disc. And that is P2T minus P1T. So I'm working out the ideal amount of work, and the ideal amount of work is the mass flux through this propeller disc, which is rho AU, and it's the difference in total pressure divided by the density, which is P2 minus P1 over rho, because the U's cancel. And if you drew a little control volume here, then why is P2 different from P1? There's no net flux of momentum out of the control volume, this little control volume right here. Why is P2 greater than P1? You tell me, come. What's the force that's acting? You don't know? The force that's acting is the force that's holding the propeller where it is. If you let the propeller go, it'd go upstream very quickly. So I have to hold it with effectively the thrust, so that the thrust on the propeller is holding it in the control volume, and there's a downstream pressure and an upstream pressure, and that they have to balance. The net force on the control volume, because there's no flux and momentum out of it, the net force on the flux on the control volume is 0. So this P2 minus P1 is exactly equal to the thrust on the propeller. And so this is an easy thing. You're cancelling the density, and the pressure difference times the area will be the thrust. And it's simply the thrust that the propeller generates. So this is an outboard motor, and it's the thrust of the propeller times the velocity through the propeller disc that is the ideal amount of work that you do. You actually do more work than that, because the flow is not uniform, and there's boundary layers, and so on. May separate. There may be all kinds of reasons why it's not an ideal, but that's the ideal amount of work, and I've worked it out for you. Okay, so now I want to do compressible one-dimensional flow for you. So you need to ask me questions, and today I'm going to do what is sometimes called Euler flow, because the viscosity is assumed to be 0, and the thermal conductivity in the fluid is assumed to be 0. So the viscous stresses are assumed to be 0. There's no heat conduction in the fluid, assumed to be 0. So this is high Reynolds number, compressible flow. Maybe tomorrow I'll say something about adiabatic frictional flow, the Fano process, mainly because of its interest to, if you're trying to push water through a sediment or oil through a sediment, you have to work it out as a Fano process. And I think I won't get to frictionless flow with heat addition. That's a very similar problem to the Fano process, and that's called a Rayleigh process. However, let's deal with Euler flow today, the first one. So, I'm interested in a small control volume here. So here's, I'm going to draw X, and here's X plus delta X, and here's my little control volume. This bounding surface, and this. And I'm going to assume that I'm going to assume one-dimensional flow, meaning that the flow is uniform at each X station. Uniform. One-dimensional flow. All right. So you could do this with your hands tied behind your back. I've got to work out mass. And that's going to be the integral over that control volume of rho u dot n ds. Well, the only places where there's any, and this is steady flow. Oh, God.
When you're using the scroll wheel, you don't actually have to click it. You can just scroll it. That'll stop it flying around it.
Oh, God. Right, this is what I was doing. So, what is it at X? What is rho u dot n at X? Well, obviously, n is this way, and u is this way. So u dot n is minus 1. And it's uniform over that area. So I can do it easily. It's minus rho times the area here, and I don't know what it is, but it's a function of x. But the area there times the velocity u is this thing worked out on that surface. I have nothing on that surface and nothing on that surface. The n is this way and this way, but there's no u dot n because u is perpendicular to n. But on this surface here, because this is only delta x different, it will be rho au plus d dx of rho au delta x equals 0. So that's that equation. It's not complicated. So it says that this term here, this cancels with that. And so this term here has to be 0. d dx of rho au is 0, and so rho au is a constant. Well, you've seen us work that out many times already. So rho au is a constant, and we're going to call that m dot. Rho au. So now, rho au is a constant, and that we're going to call m dot. So if that's true and that's constant, now I'm going to take derivatives of that with respect to x. And the smart way to do that is to take the derivatives of the logarithm of that. So take the logarithm of that, and that will give you log rho plus log a plus log u. So now take the derivative. So the derivative of log rho is 1 upon rho d rho dx. So there's the first term. Plus, well, I've actually turned it around. I've taken the next one here. It's 1 upon u du dx plus 1 upon a dA dx equals 0. So that is simply, that follows directly from conservation of mass. Rho au is a constant. You automatically get that. Now let's look at momentum. So here's my little control volume. And you're going to have to work this out for yourself. Here's my little control volume. This is A here, and here's A plus delta A here. It's not exactly the same. So I've got to work out the momentum. I've got to work out the net force on the control volume and the net flux of momentum out. That's all I got to do. No viscous stresses. So let's work it out. So on this face here, the force in the x direction is P times A. What is the force in the x direction on the control volume here? Well, it's minus because the force is acting in the minus. The pressure acts normally, and it's acting in this way on this face. So it's minus P plus delta P, and the area is now A plus delta A. Is that all there is for the control volume? Yes or no? Who says yes? Put your hand up. Who says no? Put your hand up. Good. The only one courageous enough to actually put his hand up. Why is it not? Because you think what? You don't know. Does anybody know why? Are you not familiar with control volumes? I have a feeling you're not. I have a feeling you're not, but you better become familiar. So familiar that you can do this standing on your hands. Right. So I want the reason why there's a force there and there's a force there. What about the force on this boundary? Is that zero or not in the x direction? What? Not zero. Why not? It's because the force acts perpendicular. The pressure acts perpendicular to that surface. But the surface is not parallel in general. I've said that there's a change in area from here to here. So there is some component of the force on that surface which acts in the x direction. And I want to work out roughly what it is. Well, I'm going to work it out roughly. The pressure will be P plus some average pressure, and it will be the force will actually have a component in the x direction which depends on delta A. And it's not hard to work out that if this sloping surface has, I don't have a, so this is delta A. And there's the force acting this way. And this force, and it will act on this surface and on this surface. That's the tau ki nk. So it'll be some average value of the pressure on this surface acting on delta A. So that's what I've done. I put it in there. And and now that's got to be equal to the net flux of momentum out of the control volume. So what's the flux of momentum across this surface? More or less, but not quite. The flux of momentum. It'll be the mass flux times the velocity in the x direction, right? And what sign will it have? What's the mass flux across, what's the momentum flux across this surface here? I got to work out rho u dot n times ui. But rho u dot n is negative. Ui is positive, but so the momentum flux across that boundary is minus m dot times u. And the momentum flux across this boundary is the same mass flux, but the velocity is now u plus delta u. All right, so now let's work out all these terms here. Well, this PA on this face cancels with the PA on this face. So that I got nothing there. Now what about the P delta A? Well, that cancels, that's minus P delta A. That'll cancel here. This term here is of order delta P times delta A, so it's two small quantities. So if I have just one small quantity, it's bigger than this term here. But over here, I have a delta P times A is the first order quantity, and then the second order quantity is delta P times delta A. So to leading order, if these quantities are small, it's minus delta P times A. That's the dominant term that's left here on the left-hand side. And the right-hand side will be mu and m dot u plus delta u. The leading order term will be m dot, which is rho a u, times delta u, which is simply du dx delta x. So that's my equation for this little volume. And you absolutely need to understand where that came from, because we're going to work with it now. Right. So now, what can I say here? So this this A cancels with this A here. So what have I got? I've got a delta X, and this, what is this delta P? Delta P will be dP dx times delta X, right? So this will be dP dx delta X times A, and I've got an A delta X on the right-hand side. They will cancel. So I have a minus dP dx on the left-hand side is the only term I've got here, and what I've got on the right-hand side is rho u du dx. And that's just a statement, we've seen it before, that the pressure gradient is related to the change in the velocity. And this is the force acting, and this is the change in momentum. And it's a consequence of the fact that there's no viscosity, so there are no viscous stresses. So I've written down mass, I've written down momentum. I now need to write down energy. Well, you've seen that I've said, well, one way to write down the energy for this particular case is to simply say that S is equal to a constant everywhere. I proved that. Or alternatively, I could write down the energy as minus m dot h plus a half u squared plus m dot h plus a half u squared plus d dx of h plus a half u squared delta x. Excuse me. Which gives us, of course, this cancels with this here, and so all I've got is this here. That's got to be equal to 0. d dx of h plus a half u squared is equal to 0, meaning that h plus a half u squared is constant. Well, we've seen that before. This is just like the Bernoulli equation. H plus a half u squared is constant, and it's the Bernoulli equation, but also applies for adiabatic flow that's not isentropic. So in general, we have, in addition to this, an equation of state that relates the pressure to the density and the entropy. P is a function of rho and S. Well, let's just remind ourselves, if that's true, if P is a function of rho and S, so that's an equation of state. You'll remember that we proved that S was a variable of state, terribly important. It was independent of the path if you took a reversible path from A to B. That's how we got to the idea of the entropy as a variable of state. So it says, if this is a function of these two variables, the change, delta P, is dP d rho at fixed S, delta rho, plus dP ds at fixed rho, delta S. And I've already talked today about the fact that dP d rho at fixed S will have the dimensions of a velocity squared. P over rho is a half u squared, so it has the dimensions of a velocity squared, and we're going to define dP d rho as a squared. A squared. So it follows that if entropy is constant, then dP dx will be a squared d rho dx. Now that's a tremendously significant statement. dP dx is a squared d rho dx, and it follows from this and from the definition that dP d rho at fixed S is, by definition, the speed of sound. Now, it may vary for different pressures, of course. It'll vary enormously. But it is still true that this equation will hold that dP dx will be a squared d rho dx. Or, so coming back up to this other equation that I had before, dP dx minus dP dx was rho u du dx. So let's just look at that. Oh. Right. So dP dx is minus dP dx was rho u du dx. So this says that instead of dP dx, I'm going to write a squared d rho dx. So minus a squared d rho dx is equal to rho u du dx. And therefore, in that equation for conservation of mass, instead of 1 upon rho d rho dx, I'm going to write minus u over a squared du dx. So minus u over a squared du dx plus 1 upon u du dx plus 1 upon a dA dx is equal to 0. That is enormously significant. And that means that if I multiply, I know I have to quit in a minute, but if I just want to get this for you. If I, oh, God, blimey. Beg your pardon?
I guess we can use the arrows instead of the mouse.
I'm connected with the mouse. I don't think I can. It's all right.
I think you can do this as well. So,
All right.
you can do this too. So you've got like fine tune, just shift it up and down.
Just shift it up and down with that.
Yeah, just like a little bit, yeah.
Right. Thank you. Thank you. So, here's what I really want to emphasize, is that if I use the term 1 upon u du dx, I'll have a minus u squared over a squared by 1 upon u du dx, and I am going to call u upon a the Mach number. So what I get is 1 upon u du dx. That gives me a 1 for this term here. And then I have a minus m squared, 1 upon u du dx, plus 1 upon a dA dx is equal to 0. So that is a... and so I'm reminding you that that equation, which is so significant, could have a box around that whole equation. That's true for